There we go. Trickling in. I guess this is supposed to be the last day of our nice weather for a little while. Get blustery, rainy. Maybe we'll see some snow flurries in the morning. A couple days, I guess, is next week. Fill up those lakes. Snow in the mountains. Did I get it? Yeah, okay, good. Really kind of 6 problems out of the 3, right? 2 different versions for each one of them that I put up there. Doing some substituting in order to evaluate those expressions. What do you get if X or Y are these numbers there? Plug them in. Do the fraction operations. Watch out for the negative signs. You know. Deal with the square correctly. Use extra parentheses for the negatives, right? Wrap them up in parentheses.
I can't figure out how to raise a fraction to the 2nd power.
Okay, it means multiply the fraction times itself. So, you know, if I've got, you know, I'm making up something here. 2/3 squared just means 2/3 times 2/3. Basically, you square the top number and you square the bottom number, all right? 4/9.
I guess I mean I can't figure out how to do it without a calculator.
Well, there it is, right? No, I mean, we're being smart aleck here. So if you, I mean, at this right now for all these really, we shouldn't be. Hopefully, you're not trying to use a calculator. All right. If I have, you know, -3/4 squared. Hopefully, I'm not in the middle of that, right? So you're just trying to do that operation on that fraction, and you're going to come up with a new fraction that you'll then combine with whatever else is in the rest of this expression. This is the kind that the negative is part of what's squared. -3/4 times -3/4. Negative times negative. Something squared is always positive, right? If it's 2 positives, it's positive. If it's 2 negatives, it's positive. 3 times 3 is 9. 4 times 4 is 16. So there's that part of it. And here you're going to have to do that with the 1/2. The -1/2 times -1/2. 1/2 times 1/2. 1/4. So that part of it's going to become 1/4 after you square that. Kind of getting ahead of ourselves here. We've still then got the -3/8. Luckily, whoops, thinking of the 8 there. In this one, it's multiply, so you don't have to, you know, get a common denominator. Remember, for multiply, you don't need a common denominator. You just maybe look for things to cancel, but then you multiply it across. Did that help, whoever that was? I'm sure. I'm not sure.
Yes, thank you.
Okay, okay. Let's see, where's my erasing rag? Can I find that? There we go. All right, let's get this out of the way for the moment. And let's see, I stuck that in the middle there. And this also. Should I wait a bit? Should I wait a minute for you guys, or should we get going? Just say, please wait, or go ahead, or whatever.
Can I have just one more minute, please?
A couple more minutes. All right. Yep. See how much that can get done before we start. So we're ready here. Ugh. It seems like my lighting is off today. Or it's either glare or dark spots. Yeah. Whatever. As long as I'm not blocking it over there. See, then I get that glare. If it's a problem, let me know. It's my problem. For all of these kinds of problems, your first step really is to substitute the given value in for the variable. If it is a negative number, wrap it up in parentheses because you're likely to be doing something else around it. Now, as soon as I say that, realize, oh, this one, there is nothing directly attached to it. -7/4 plus 3/4. That would be fine without the parentheses, because that really is a term that stands all alone. There's no coefficient, there's no multiplier connected to it. So there's our substitution. This is the one I kind of maybe call it the easy one. I gave you a common denominator. So we really will end up with a number of fourths, because that's what it broke it into. -7 plus 3, -4. And we probably reduce that to -1. Is that okay? Kind of squeezed too many things on the board here. I'm going to erase as I go. So, am I okay with that one? Here I go. Shout out if you need me to wait. All right, so the next one, x is supposed to be a 5/8. Plug it in, 5/8 plus 3/4. Okay, here we're trying to add those two fractions, and I need a common denominator I don't have yet. Looking at those two numbers, I might hope they're small enough you recognize that 8 will work as a common denominator for the 4 also. Frog in my throat here. To get these to be both 8s, right? I need to multiply, this one doesn't change. I'd have to multiply this by 2/2. That special version of the number 1. So that makes this a 6, huh? And usually we like to show steps vertically here, but I've squeezed things in on the board. 11/8. And I double check. That looks like lowest terms. That's good. Here we go. Keep going. All right. In fact, I might erase that whole top row, so I have more room as I go. Okay. Here we go. Yeah. This one, we're going to put in a -2/3 to start. So 1/2 minus -2/3. We are going to need to get a common denominator. You can kind of do this now or later. You might notice, oh, that's subtracting a negative. That's going to be the same as adding. If you want, you could change it right now to an addition problem. That rule still works with fractions too, you know. That almost looks easier. All right, so I need common denominator. Looks like it's going to be a 6. So 3 over 3 will get me 3/6, and 2 over 2 will get me 4/6, 7/6. Shout out when we have trouble. Here we go. It's throwing that 3/4 there. Same thing here. 1/2 minus 3/4. Which number is bigger, 1/2 or 3/4? Just, you know, I bet you know. It's just, we're going to do more of that today.
3/4.
Yeah, do need a common denominator, so let's get it to be 4s, okay? So 2/4 is 1/2 minus 3/4, 2 minus 3, -1/4. Slow down, Steve. Is that okay? So my point on that one was putting a negative sign in front of the x and then negative for that first example. Excuse me. Get that congestion, and once you start talking, then it moves. Too much information, sorry. All right. And next one, all right. 3x squared. Y, I'm gonna plug in, first of all, let's do, oh yeah, I did 2 different versions, right? If I make y, make x a 1/4. 3 times 1/4 times 1/8. Remember, I was making this up thinking, oh, let's make the numbers work out pretty nice for common denominators. I don't need any common denominators, do I? This is a multiplication problem. At most, we would look to see if we have any common factors to cancel before we multiply so that we have less work to do at the end. You might think of this as 3 over 1, just to make that real clear. But I guess that's just 3, 1, 1 is 3 over 32. Okay. No, Steve, that's not okay. What did I do wrong?
Are you supposed to square the 1/4?
Yep, I just caught myself looking at the next one. Back it all up. Sorry, erase your math. 3 times, I do want this parenthesis now. I really maybe don't need it because it's not negative, but it's cleaner looking. Duh, that was my bad, sorry. Now, don't forget your square. The teacher says. All right, so let's do the square. I'm going to write that as 3 over 1 anyway, all right? Because I'm next to a bunch of fractions. What's 1/4 times 1/4?
1/16.
All right, 1 times 1 and 4 times 4. And this is 1/8. 3 and a bunch of 2s, right? Nothing to cancel. So 3 over 128, I think. I did a little mental math there. But
Correct.
okay, good. It's a multiple of 2, 2, 2. It's like 2 to the whatever, 7th or something. All right, and the last one, the other version of that I made up, let's put in those other 2 numbers. Just the thing about this one, it's got that the negative signs in them. Okay, so 3 times -1/2 squared and -3/8.
I was a little confused with the -1/2. So would that would just end up being a positive 1/4, right?
Exactly. Yep.
Thank you.
Yep. That's one I did on the side a second ago. If the negative sign's inside the parentheses, means you're actually squaring that negative also. Negative times negative, that's going to turn to the positive 1/4. Yes, absolutely. Made that look like a fraction ready to go for myself there. So how about 3 times the 1/4 we just talked about, still -3/8 here to deal with. Again, nothing to cancel. But positive, positive, negative, I'm going to end up with a negative number, right? 3 times 3, a 9. There's my 4 times 8, 32. Remember, 4 times 9 is 36. Don't try to cancel that. So, little practice with that evaluation stuff. I got a good question. Oops, here's somebody waiting to get in. Let's see if we can get her in there. Yep, good. From one of you, a similar kind of problem, kind of challenging. I'm going to ask you to look at the notes I posted in the forum today. It's an attachment, a Word document. I've kind of worked it all out and explained it. But it's a similar kind of problem. Something that looks like that actually has a negative sign in front, and then they give you a number for x, a fraction. You know, so just like we did, you're going to plug in your fraction and square it, and plug in your fraction, whatever fraction they give you in your problem. Now, the problem I worked as an example was one that somebody asked me about, and so there's going to be perhaps different numbers in that version than your problem in your homework. I'm referring to number 11 in the 1.5, 1.6 homework, okay? But go look for my answer, my write-up in the forum, please. And if you still get stuck and can't figure it out, send me the question. I'm going to ask you to try it. You're on your own first. Okay. So, going on. We're going to try and get through 1, 8, and 9 today. It's really kind of a lot of show and tell, that is more than usual, talking about different properties, relationships, and then some different kinds of number sets that we want to be able to describe or talk about. First, just a real quick addressing 1.7. I mentioned we don't actually assign or study this much, but you just want to be comfortable with the concept of place value for the decimal places. You know, if it says round, for instance, round to the 100th place, you know, which decimal place is that, right? The ones are always ones, they're whole numbers. And then it's tenths, it's like 1 over the power of 10, right? Tenths, hundredths, thousands, and so on. If you were adding, or subtracting, remember you line up the decimal point. I can just write this like that, right? Line up the decimal point. Now, if you're using it, I know you're going to use calculators. They're designed to work with decimals, so it makes it pretty easy for you. Notice there's nothing over here. You can always put in a placeholder 0. It makes you feel better about it. And just bring down that decimal point. Same with subtraction. And sometimes you have to do the borrowing, and just like any arithmetic problem. The other one just addresses, you know, what if I'm multiplying two values that have decimals in them? What you want to understand without much explanation, I guess, is your final answer will have the same number of decimal places as the total in the two numbers you're multiplying. So 1, 2, my final answer is going to have 2 decimal places. So that helps me to know where to put the decimal point. Otherwise, I'm going to multiply this just like there were no decimal points in it to start. 3 times 7, 21, 15, 16, 17. 1 times 57. And so 1, 14, 5, 6, 7. 7, 4, 1 are my digits. And that first rule said I need 2 decimal places. So these last 2 digits are to the right of my decimal point. There's my 2 decimal places, the combined 2 places. And then it's always, you know, nice with decimal problems like this to maybe do an estimate. You know, this is a little more than 1 times almost 6. A little more than 1 times 6. Okay, we're in the ballpark, right? Probably did it right. Division, just the last thing that we're going to move on from this. If I have a division problem,
So you said we're not going to cover this, that we have to learn this on our own, correct?
yes, if you really haven't worked with this much, you're going to use your calculator for most of this. And I think next
I
check,
never learned decimals ever, so I'm still trying to contemplate even what you're trying to teach me right now.
yeah. Okay. Well, section 1.7 might walk you through it, and if you want to practice and try some of those,
I'm going to need to, yeah.
send me some questions, and I'll be glad to help you. Okay.
Also, I just want to mention that I have a lot of notes from last term that went over this that I can send to anybody who needs help.
I'm sorry, if you would just start that over. I had a hard time hearing much of that. I turned up my volume.
I covered a lot of this last term, and I still have all of my notes from that. I feel like I've just been going back and kind of checking those out, and I can send them to anyone who needs that help.
Yes, if you were in Math 20, that is a section that you spend much more time on there, covering that. The idea here is, I think perhaps, is that as we get more into algebra, manipulating these things with the variables in them, we don't use decimals as much. We're really working with the integers, whole numbers, fractions most of the time. And in a word problem, you might run into a decimal value. Like I think I said yesterday, especially if you're dealing with dollars and cents, money. But most of our relationships are built around these fractions and integers, and not really mixing in the decimals too much. So we don't spend a lot of time on it. If you're spending time on it, I'm here for you if you want to send me questions. All right, that's an important point. If I'm trying to, here's just the last review, right, refresher. If you're trying to divide by hand with a number that has a decimal in the divisor, what you're dividing by, basically we want to get that decimal point out of this number, because it kind of gets it too messy to, where's the decimal point going to be in my answer? So this is like this number, right? 135 divided by 2.5, a fraction. I'm going to multiply the top and the bottom by 10, and I get to this equivalent fraction with no decimal point. So basically, we're going to do the same thing here, probably in our heads. But if I multiply this by 10, it moves that over 1. If I multiply this by 10, it's going to move it over 1, so I have to put in the 0. Now, if you were typing this problem into your calculator has no problem with decimals. 135 divided by 2.5, it would be just fine. It would give you a good answer for that. But here, if I was trying to work this by hand, I would try to get the decimal point clear out of the divisor like that. If there were 2 decimal points up here, I'd multiply by 100, move it over 2 places, move it over 2 places on both of those values, the inside and outside. Now you're ready to go to work. And I know long division is everybody's favorite, almost as much as word problems. Okay. Should I do that just because I'm going to do that? I know long division.
Yes, thank you.
Yes, I know long division is not everybody's favorite. I have 2 digits. You start by comparing it to the first 2 digits. Here, how many 25s can I get into 13? None, right? Not a big enough number. So then I compare these 2 digits to the first 3. How many 25s fit inside of 135? Well, 4 of them gets me 100, 5 of them gets me 125, 6 would be too big. So 5 times 25 gets me 125, and I line it up just like that. And the 5 that I multiply by, I put it right above that column where I ended, and that's the beginning digit in my answer. So you figure out how many of that you can get in there without leftovers, right? Or without, fractions. And you do that multiply and write it there. Now you subtract. It's always subtract at this step. Looks like I get 10 left. This should be smaller than that, otherwise you didn't get enough out of there. Right? This should always be smaller. So it is 10 smaller than 25. And you always bring down your next digit and you do that process again. How many 25s can I get into 100? Well, I made this up. How nice. Works out exactly 4 of them. 4 times 25 is 100. Subtract again. There is no remainder or leftover. 25 times 54 turns into 1350. So that was a little quick review there, a quick show and tell. If you are trying to practice some of that, get started, do some practice, send me questions if you want some help. But we're going to move on.
Thank you.
Yes, you are welcome. All right. And change papers here. All right, 1.8. The real numbers, huh? Well, it's just a name. The real numbers. Historically, these sets of numbers that we've been working with all got clumped together and called the real numbers because eventually they invented something that they decided to call not a real number. You don't have to worry about those, but anyway, I'll tell you when we get there, okay? So we're going to learn about a new kind of number today and give some names to some others we've been working with. So first of all, what number, I know it looks like an equation, we haven't done that. What number can I square? What number can I square and make 25?
5.
5.
5.
So x could be a 5. Is there any other number times itself that gets 25? Trick question.
One.
How about the negative one? Because negative times negative would also be positive 25. You buy that, right? We've been just talking about that kind of thing a lot lately. Squaring the negative turns positive. So the point here is there are 2 numbers I can square and get 25. That's sort of the definition of these numbers we call square roots. Squeeze it in. And similarly, negative 5 is a number I can square. So we say here if n, I forget if it's n or m in the book. If some number can be squared and to get this one, then we say m is, like up here, m is the square root of n. Okay, so definition. Square root is the number you can square to get the other one you're talking about.
Are we going to have problems like this on the tests or quizzes?
Yes, you're going to need that. Not so much like definition, but you're going to need to be able to use what we're talking about here. So, what numbers can I square and get 9? What would the square roots of 9 be?
3.
Yeah, just trying to think of some familiar ones to begin with here. Right? So there are 2 values. There's always 2 of them you can square. Right? The square root could be a 3 or it could be a negative 3. What can I square to get 4? But to get 16.
4 and negative 4.
Yeah, there you go. All right, so that's the concept. What's the number you square to get this? Now we need notation. How do we describe that? Write that, right? So we have this thing that's not quite the division bar, right? It looks like a little check mark with the bar on the top. This is the square root operation symbol. And so Then we put our number inside that we want the square root of. This is basically saying, what number can I square and get 25? Now, already we talked about there's always two numbers, positive or negative. This one always refers to the positive square root. And hope you'll allow my abbreviation there. So this means what's the positive, or otherwise they call it principal, the main one, right? Principal square root. What's the positive number I can square to get 25? 5. If I want to designate the negative one, I have to put a minus sign in front of it. What's the negative number I can square? Basically saying do the inside first, and it's like it is a grouping symbol, okay? Find that positive square root, and now let's use the negative. This one's the negative 5.
I have a question.
Yep.
So for the testing quizzes, do we need to memorize the definitions of what you're saying or just understand what the concept is?
Mostly understand the concepts for how to use these things. What are they asking for? This is asking for the positive. This is asking for the negative. Now, 1.9 today, we're going to talk about some properties where, we might use the term, find the inverse of 5. Huh? Okay, got to know what inverse means. We're going to get there today, all right?
Okay.
So you have to understand the definition, but we're not going to ask you to write out definitions.
Okay, thank you.
I'll give you that. All right, so, just more of those, it's square root of 100, or square root of 36, or the square root of 81. These are all the numbers inside that I'm using for examples right now are all what we call perfect squares. They are the square of some integer value, right? 10 times 10, right? Square root is a 10. Square root is a 6. Square root is a 9. Math facts, huh? Doing fractions, kind of going backwards from some stuff we did today. This is kind of like saying, like somebody that started, we said, what do I get when I square this fraction? How do I square the fraction? Well, we're going backwards. How do I unsquare? That's what this is doing, right? How do I unsquare this fraction? What do I square to get a 4? And what do I square to get a 9? It's really kind of like saying square root of 4. It is saying square root of 4 over square root of 9. What's the square root of 4? A 2, a 3. I can go backward and say, oh yeah, 2/3 times 2/3 does get me the 4/9. So the number that you square to get what's inside, that's the square root number. That's a square root. Okay, hold that thought, all right? Now, some of them don't turn into nice integer values. What number can I square and get 5? You probably want to find that key on your calculator just so you can use it sometimes. Most calculators have something, I think it's your x squared button, and the second function is square root, or maybe it's vice versa. But you gotta look at mine. Yeah.
My calculator actually has a square root button.
Yeah, okay, a separate, yeah. On my little one like this, this is the square root is the opposite. It's like the, if you look at a calculator like this, and there's usually 2 different functions on each button, and you have to do the second function to get the other one. Those operations are usually opposites of each other. Here's square a number, and here's square root that number. Anyway, on this calculator, it's over on the left side. But what I was getting at is I could type that into my calculator and it'd tell me it's 2 point something, 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 and it'll show me as many decimals as I have my calculator set to show, but it's never going to work out evenly. There is no nice decimal rounded decimal number exactly that will square to 5. So anything I might actually use in the real world would be an approximation. 2.3 something or other, I'm just making up, would be an approximation. But this value, the way I wrote that, it represents a quantity, right? It's on a number line. It's somewhere in here between 2 and 3, right? It's got a place, it lives on the number line. Just can't kind of write any more exact version of that number. So this is the most exact notation for that concept. The square root of 5, I can generally know it's between 2 and 3. I can get a decimal approximation. The calculator knows a technique for getting close to it. Gosh, we used to do that when I was in school way back when. Talk about long division. How about doing square roots by hand? That was weird. All right, history. Before calculators, way back when the TVs looked like this, right? Square boxes, they really did. All right, Steve, stop it. Okay, oh yeah. Just had a birthday, my sister sent me a bunch of old family pics, and there we are sitting around. Really, the TV was like this big, and it was a cube. It was a cube that was this big, and we watched black and white TV. Anyway, I'm old enough. That was back in the late 50s, 60s. Okay, so that kind of number doesn't work out evenly, right? Square root of 5, square root of 11, square root of 10, there is no exact nice number answer for that. Certain kind of, it falls into a different set of numbers than all those nice ones. That's what we're going to talk about right now. Okay, number line, sets of numbers. When I started this term, I kind of said, well, if you were going to naturally count something, 1, 2, 3, good. Count, you probably start 1, 2, 3, 4, right? The counting or natural numbers, right? The counting or natural numbers. Counting or natural numbers is that set of, start with 1. When we added the 0, we added the whole. We got the whole numbers. All right, we got the whole numbers still over there. We added the opposites of the whole numbers. The whole numbers and their opposites. We got the set of integers. And that's a number, that's a term I use a lot because not everything's positive. But we do like integer answers. A whole number or a negative whole number, negative, the opposite of a whole number for an answer rather than messy fractions. If we can, doesn't always happen. Then this last section, we started working with, the ones in between, the fractions. One term for a fraction is a ratio, right? It's a ratio, a comparison of two values, a ratio. That word is the root of the set of numbers that we call this. This is a rational number. Anything you can write and make look like a fraction. There's important. If you can make it look like a fraction, it's a rational number. You can turn it into a fraction built out of integers. So obviously, like my 2/3, negative 5/8 just happens to be a negative fraction. 4, we've been turning those into fractions when we're using them with something else. So watch out, those whole numbers, integers, they can be fractions. Then we get a little trickier. Square root of 9. Can I make that look like a fraction? That's just a different way to write the number 3. That notation stands for the quantity 3, which I can make look like a fraction. So some square roots simplify into numbers we can call rational numbers. kind of backing up right now. Notice this is like Russian dolls, right? These are all, countings are all whole numbers. Whole numbers are all integers. Integers are all rational numbers. Everything's inside. In fact, a common sort of Venn diagram is to show them all like this. And there's the counting numbers and the whole numbers and the integers and then the rational numbers. Right? Now that doesn't represent relative size of those sets, just how they relate to each other. So just a little bit more about actually, we're going to come back to that. Spend a little more time there for a second. Well, what about this kind that I can't simplify and make look like a fraction, a simple fraction? Well, our definition or name is a negative of that. These are called irrational. All right? Not rational. Irrational numbers. That's a completely separate set, right? It's not contained, or none of these are. Everything else was a rational number, and now I've got this set of numbers that I can't make look like nice fractions. That's the irrationals. And there's a lot of them in there. You could say there's more than the regular fractions, maybe. It's like they're both infinite size. How do you count that? Mathematicians try. There's a nice famous one that we use a lot. 3.1459. Remember that number? What?
Hi.
Pi, right?
Pi.
Never repeats. This decimal never repeats, never stops, never works out even. Pi is defined as a ratio of the diameter of a circle to its circumference, right? It takes 3.14 of those things to get all the way around the circle. But anyway, that's the definition of pi. But that is a famous irrational number. It's an irrational number. Anything that, okay, don't get too messy here. There are lots of irrational numbers. We can kind of make up some, but anytime you get a decimal that doesn't have a pattern, I guess we're gonna come back and talk about that, or doesn't stop, it means it never works out evenly, you might say. It's an irrational number. Any non-repeating, non-terminating decimal, terminating, stops, is an irrational number. You can make up weird patterns. There's usually like a textbook thing. 1 0 1 1 0 1 1 1 0 1 1 1 1 0. Now there's no real formula for getting that. I just made up a pattern, but it never stops. It's an irrational number. So there's a lot of irrational numbers, just like a lot of fractions. They're in here too. They're still all on this number line someplace, right? Well, 2 point whatever, it's on there someplace. Mix them all together. These combined, all of those rational plus irrational numbers are the set of real numbers. Everything that we will work with in this course is a real number. It could be located approximately on the number line, the real number line. It's a real number. Okay, I got to talk about rational numbers a little more. That definition, anything that can be made to look like a fraction of integers, a ratio of integers. So a couple of weird ones with decimals, basically. You know, decimals are just a shortcut notation for dividing by powers of 10. What place is that? That's the 10ths place. So I can make a fraction over 10 if I just divide if I drop the decimal point. 13 over 10, right? More than one. 3.52. 52 100ths or 10th hundredths place. I can turn this into a fraction by making the denominator the hundredths place and then drop the decimal point. There's a fraction. Okay, I can make it a decimal. decimal value that terminates or stops, I can figure out what's that last place value to use as my denominator. We just looked at one though that never stopped, right? Pi. So it can't be a rational number, but any terminating decimal is a rational number. We could find a way to write it as a fraction. Terminating, stops, right? Then there's ones like 3 forever. What fraction is that? You know that?
1/3.
Huh?
1/3.
Yes, yes. In fact, if you were to take your calculator and do 1 divided by 3 right now, it would do 3s as long as for as many places as you've got on your calculator, unless you've told it to stop after 5 or something like that. Yes, so here's
1/3 from that.
a decimal that doesn't stop, but it's got a repeating pattern. All right, so again, a special decimal form if it's a repeating decimal. If it repeats forever, a pattern, there's a way to make it look like a fraction. It's not important if you know how, but that you understand a repeating decimal is a rational number. There's a way to make it look like a fraction. So sometimes that pattern, whoops, is multiple terms, you know. I'm just making up something. Right? Whatever this might be, 2463, 2463, 2463. There's this repeated pattern. That's what that bar across the top means, okay? If I haven't said that yet, right? We identify the pattern or the part that's repeating, and then we usually only present it once. This much is going to repeat over and over and over and over and over. And so this is a repeating decimal. It is a rational number. There's a way to turn it into a fraction. So homework problems will give you a list of numbers, you know. Which ones are rational numbers? Which ones can you make look like fractions? Whole number? Yeah, I can write it over 1. Fraction? Yeah. Terminating decimal? Yeah. Square root that I could simplify and make it look like a fraction? Yeah. Square root I can't simplify. Irrational. Decimal that doesn't end. No repeating pattern. Irrational. You'll see homework problems like that. Okay. Talking longer than I expected. It's all right. Means we'll finish up 1.9 on Monday. It's okay. And I wanted to then, as a way to practice these different kinds of numbers, you'll see homework problems that list like a bunch of these and then choose which sets they belong to, or find all the whole numbers, or you know, which set of numbers does, do that. Which set of numbers does -2/3 belong to? Is it a counting number? Well, no, it's not 1, 2, 3, 4, 5. Is it a whole number? No, it's not 0, 1, 2, 3, 4, 5. Is it an integer? No, it's not a whole number or one of its opposites. Is it a rational number? Oh, fraction? Yeah, I can make it look like a fraction. It is a rational number. Is it a real number? They're all real numbers that we're working with.
Yes.
Yeah, so that's what you say. So what's this other thing, since I mentioned it? If it's not a real number, what is it? There actually is mathematically some sort of number that's, what can I square and get -5? Right now we should be good with the idea that positive times positive will give me a positive number. And negative times negative also gives me a positive number. So there's no number times itself. There's no real number times itself that gives me a negative. I have to have opposite signs usually. But it's like going into another dimension or something. Mathematically, they exist, and actually there are technological applications, particularly understanding computer charges within the chips and stuff. But they use they're called imaginary. Imaginary. Square roots of negatives are called imaginary numbers. They're not reals. So there's that big set of real numbers, and if I put a negative sign inside, that's an imaginary number. Notice that's different than this. That's just an irrational number on the left side of the number line. So you shouldn't run into those in our course, okay? So last thing, we're about out of
You
time.
don't have to worry about what you just said, right?
Exactly right. You shouldn't have to worry about this, but just since I mentioned real versus whatever, I thought I'd present the whatever. Yeah. This one you got to know, oh, that's the negative square root of 5, whatever it is. It's a real number on the left side of the number line sometimes, between -2 and -3. There's a group of problems, and I'm out of time, in 1.8. If you're going to give them a try, where they list a bunch of fractions and mix in a couple decimals and whole numbers, and they want you to put them in order. Like, draw yourself a little number line to figure out where do they go, which one's the smallest, and which one's the largest. And they want you to order them like from, 1, 2, 3, 4, 5, 6 numbers. Put them in order. We'll practice that on Monday. I'm out of time. Feel free to send me questions if you're trying and you get confused. But we'll work on that some more. And then we'll finish up 1.9 and go on to 1.10 on Monday. Okay, folks. Well, it was good. We sound like we needed to do a little that 1.7, and I guess I take more time than I imagined on 1.8. So have a.
I have questions to ask after. I have questions to ask after class. Can I stay?
Absolutely. So I'm
Thank you.
going to release you all, and happy weekend, and I'll see you Monday morning. Send me the questions you have. Try that homework as usual. And if you want to stick around, yep, I'm good. I'm here for a while. I'm glad to be here.
Don't erase that. I just have a question regarding that one. Sorry, Kaylee. I just had it on the board. I just wanted to ask.
You're good. It's fine.
You had that that square root with the -5 inside. That you said was an imaginary. We don't need to worry about that. But if you have the negative sign outside of the square root with the 5, that is something that I need to know, correct?
So yes, correct. The one with just square root is saying, what's the positive number?
Okay.
This one's a 3. The one with the negative saying,
Negative.
find the square root and then make it negative.
All right.
So yes, you need to understand that.
Thank you. Thank you very much.
Yes, very good. Yeah, see you later, folks. Feel free to log out. And all right, it's the Kayleen show now. Ha ha.
Yeah.
I'm sorry, I'm just teasing you.
No, I don't care. It doesn't bother me.
I don't.
Little things don't bother me. Like lasagna doesn't bother me.
Thank you. I hope you don't mind me teasing.
No, that's my nickname. So.
Go ahead with the questions, please.
So on homework 1.9.
Okay. Oh, 1.9. Oh, yeah. Okay.
Sorry, I'm a little bit ahead. I got confused, but I figured it out. So can we try some of them and see if I can get it again?
Okay, so I'll give you like a real quick lesson before we try something, okay? I looked at your homework for 1.9. I think they were almost all distributing problems. Am I right?
Okay.
Yeah. So this expression is saying I want 2 times everything that's inside. This is written like x plus 5 and plus x plus 5. So I get 2 of the x's and I get 2 of the 5's. So the shortcut is say, oh, I want 2 times that number and 2 times that number. The outside number multiplies every term that's inside. So
I understand that.
all right. And then we throw in a negative sometimes, and that makes it messy. So if that's the gist, that's the basic principle for the distributive property. What's your harder example?
Question 10 on the homework is 2 parentheses 8x squared minus 5x plus 6 parentheses negative in the middle, like negative, and then parentheses 3x squared plus 7x minus 9 parentheses.
All right.
Yeah, that one kind of confused me, and then I figured it out. I was like, huh?
It's well, it's a good one to we have to understand, right?
Mhm.
This one, first piece, this is one term.
Mm-hmm.
Has a big bunch of stuff inside, but right, one piece and 2 pieces. This one is saying 2 times all of those, just like the earlier one, the easy one I made up a second ago. Okay?
But then do you square it too? No? Okay.
This is just the numbers times numbers. 2 times that is going to be 16 of those things now.
Okay. That's what my confusion was. I didn't know I wasn't supposed to square it.
Okay? So 2 times the coefficients or the numbers.
Hmm.
This one, though, is interesting because of the negative. Here, if I had a number out here, I almost like to start that way, because now I could say it's -3 times each one of those, right? So it's negative times the 3, negative times, and then it's always the negative times the negative that people forget and mess up. This one, there's no other number visible. You have to assume a 1. Basically, you're changing the signs. Negative times 3, negative times 7, negative times -9. So you distribute the negative sign to each one, or think of it as -1 times each one of those.
That
Okay?
makes more sense. Yeah.
Okay.
And then I have also 2 more questions, but they're not like they're not problems like that. Or do you want me to finish it? Do you want me to finish that?
There I did the distributing, right? I just finished the distributing, and now there's a bunch of like terms to put together.
Yeah.
Some x squares and x squares, and here's some x's and x's and some constants. So you combine those.
Yeah.
If that's
And
good,
then
let's go on, all right?
okay.
Looks like you're the only one left.
Yeah.
You.
Yep.
What else? Next.
Well, can we start the chapter review thing early?
Oh, absolutely. I think.
And is that the test also?
No. I mean,
No.
no, the test won't appear in MOM until.
Oh, will it? Okay.
Until
So it's
test
not
day.
ahead.
Right. You can. The reviews are reviews, and I will always strongly encourage folks to do the reviews. The
Yeah.
text, the MOM review is actually going to look a lot like the MOM kinds of questions because they're drawn from the homework.
Okay.
The optional one is a worksheet that you could pull out and do on the side. It's usually got the answers with it. If it's not, again, like I mentioned yesterday, there's lots of settings I have to update every term. If it doesn't seem to be accessible, let me know, but it should be available to you to work on.
Yeah, I was gonna work on it today.
Yeah. Yeah, get started. Why not?
Mm-hmm. And then you said there was a question on the forum, like x squared minus 3 plus 4. Where is that?
Somebody asked me a question,
Oh, somebody. Okay.
an
Okay.
evaluation question like those first ones,
Mhm.
and I wrote up a nice, work explanation, and I put it on a Word document. So for everybody's sake, I posted that Word document in the week 2 discussion this morning. So everybody can go in and look at my explanation for that number 11 in section 1.6.
Okay.
Yeah.
Perfect. And then
And
can I
the numbers
please?
will be different, but you can follow the mold I created,
That's awesome. That's very great. It's very grateful. Thank you.
Yeah.
Nurse.
It helps. So I do. All right, Kayleen, then enough for now.
Yeah, I'm good. All right. Thank you.
You're very welcome. Have a nice weekend. See you Monday.
Bye.
Okay, bye.